Hello everyone, welcome to this lecture video tutorial in Calculus 3. Enjoy learning. Hello everyone, in this lecture video we will discuss the definition of the power series as well as the definition of the radius and interval of convergence for a power series. We will also illustrate how the ratio test and group test can be used to determine the radius and interval of convergence for a power series. Okay, for our first definition, this definition, and you are given an infinite series that can be written in the form summation of c sub n times the quantity x minus a raised to the power of n, where your n starts from 0 and up to positive infinity. This is called a power series. In the variable x centered at constant a, so as you can see here. Before we proceed to this theorem, I will give a note with regards to the definition of the power series. Okay, so it's up here. So the note here. Okay, note number 1. We take x minus a to the power of 0 to be equal to 1, even when x is equal to a. This is of course for convenience. Okay, in writing the general form. So remember that this is the first term of the power series. If you expand this summation here, this one, okay, so you can write this as c sub 0 x minus a to the power of 0 plus c sub 1 x minus a to the power of 1 plus c sub 2 x minus a to the power of 2, and so on and so forth, up to c sub n x minus a to the power of n plus dot dot dot. Okay, so this term here, this one, we will denote this as equal to 1 even if x is equal to a. So we have 0 over 0. So as you can, if you recall your calculus 2, when we talk about indeterminate forms, you can have 0 to the power of 0. So this is not the case when we are discussing about the power series. Okay. Second note, here, if your x is a particular number, okay, the power series becomes, if you recall, becomes an infinite series. Okay, infinite series of constant terms. Okay, so remember, if you look at the definition, As you can see here, if this is a number, our a is a number, if this is a number, then it will become an infinite series of constant term. So that's what we discussed last time. Okay, in lesson 1. No, lesson 2. Okay, number 3. If phi is a function of x, is a function of x, then there are power series of the form. Okay, so if you replace your x there in definition above, we can write it in this form: summation of c sub n phi of x to the power of n, where n starts from 0 to positive infinity. Okay, so if you try to expand this, so mean to say this is a function. Okay, you can put a linear function, a quadratic function, a cubic, and so on and so forth. So this is more general than the definition of the power series. Okay, c sub 0 phi of x to the power of 0 plus c sub 1 phi of x to the power of 1, and so on and so forth up to c sub n phi of x to the power of n plus, and so on and so forth. Okay, such series is called a power series in phi of x. Okay, so let's now write our goal. The goal of this lecture. So our goal here is, since we can think of a power series as a function of x, as a function of x, as you have noticed. Okay, function of x, say this one, this notation. This is our domain, mapping from the domain d sub f to r, given by this notation c sub n x minus a to the power of n, and starts from 0 to positive infinity. So we ask ourselves, okay, for what values of x, okay, values of x, if any, does the power series, okay, converge. Okay, so meaning to say, for a given x and you evaluate this power series, so meaning to say, if this series is convergent, then that x now is one of the element of the domain of the function. Okay, so to find the domain, all you have to do is to look at the theorem above, see and understand the theorem above. Okay, so this theorem that I am talking is this one. This theorem, as you can see here, okay, the convergence of a power series. So you're given a power series and exactly one of these three will hold, meaning to say it will only, the domain contains only one number. It is a singleton set. It converges, the series converges only at A. And the second one is if you can find a number R which is greater than 0, such that the series converges absolutely for in this interval, and diverges if this is this interval here. And also number 3, if the series converges absolutely for all x. Okay, and this R here is what we call the radius of convergence, and this interval is what we call the interval of convergence. So for the case 1, if the domain is a singleton set, then the radius is 0. For number 3, for case 3, if the series converges absolutely for all x, then the radius of convergence is infinity. Otherwise, there is a particular number. So we can use case 2. Okay, so that's what we mean by how to get the domain of the power series. Okay, so let's have an example for illustration. Okay, this one, example number 1. Example, we are going to find the radius and interval of convergence. Interval of convergence. Okay, so example number 1, we have summation of n factorial times x to the n. Your n starts from 0 to positive infinity. Remember that this is the same in the idea of the infinite series. It doesn't directly starts at 0. It may be there are problems that it will start from 1, 2, or 3. Okay, so solution. So as I've said in the introduction, we will use the idea of the root test or the ratio test to find the interval of convergence, or shall I say to find which x does the series converge. Okay, so first is we have to let our a sub n, which is equal to n factorial times x to the n. Okay, then by root test, then by ratio test. Ratio test. Okay, I know that you have now the idea on how to choose what test to use. So when you are going to use the root test, it must be that the given problem is raised to the power of n or something. Okay. Okay, so take the limit. The limit of this is in the root test, as you have in the ratio test, as you have noticed, if you recall your the theorem with regards to this test. It says there in one that the the the, the series is convergent if it is less than 1. Okay, so meaning to say, what we will do here is we will choose the theorem 1 in the ratio test, because as you have noticed, we are going to find those x for which the power series converges. Okay, so substitute, replace n by n plus 1. So we have n plus 1 factorial times x to the n plus 1. Our denominator is a sub n. We have n factorial times x to the n, where n approaches to positive infinity. Okay. Okay, simplify. So this will become n plus 1 times n factorial. This is x to the n times x. Copy the denominator as n approaches to positive infinity. So now we can cancel out n factorial and x to the n. Okay, so what remains here will be the limit of n plus 1 times x as n approaches to positive infinity. Okay, by the definition of the absolute value, you can factor out x here, because as you can see, the limit is n, so we have here, what will remain here is we have this one. Okay, we will disregard the absolute value symbol because our n starts from 1. Okay, this is always positive. And if you take the limit of n plus 1 as n approaches to infinity, notice that this is positive infinity. So what we will do here is take a particular case when x is equal to something. Okay, so when x is equal to 0, this one becomes n plus 1 as n approaches to positive infinity. This is 0. So for whatever number this is 0. Okay, while when x is not equal to 0, the value of this expression here on the right hand side, we have as n approaches to infinity, this is positive infinity. Okay, so what does this mean? It follows that the series is divergent. Okay, divergent for all x, for all values of x except 0. Okay, so when this is 0, this is less than this one here. If this is 0, this is less than 1, and this means that it is convergent. So since we are going to find the radius and the interval of convergence, so we are going to state it here. Moreover, our r here is 0. This is the radius of convergence, convergence. And the interval of convergence is this set. Okay, interval of convergence. It is a single tone. Okay. Okay, so we are done with example number 1. Let's now try to have an example. This is, by the way, this example illustrates the theorem for case 1. Okay, let's try case 2. Let's have some example here. Okay, example number 2. We have summation of negative 1 to the n plus 1 times 3 to the n x to the n over n times 5 to the n. Our n starts from 1 to positive infinity. Okay, again, in this example, we are going to let our a sub n, which is this one here. We have negative 1 to the n plus 1 times 3 to the n, okay, x to the n over n times 5 to the n. Okay, so again, by ratio test, we will not use root test. Okay, ratio test, we have in the limit of a sub n plus 1 over a sub n as n approaches to positive infinity. Okay, substitute. So for our numerator, we have replaced n here by n plus 1. So we have negative 1 to the n plus 1 plus 1, and then we will have 3 to the n plus 1 times x to the n plus 1 over n plus 1 times 5 to the n plus 1. So the denominator becomes the same, raised to the power of n plus 1 times 3 to the n times x to the n over n times 5 to the n. Okay, so simplify. What we will do here is we reciprocal. We use reciprocal here. What happens? So let's try to write this in this form. First, times 3 to the n times 3 times x to the n times x over n plus 1 times 5 to the n times 5. So factor out, and then in the denominator we have n times 5 to the n. The denominator here becomes the numerator. We have negative 1 to the n plus 1 times 3 to the n times x to the n. Okay, so let's cancel out this one, and cancel out this one here, also here, any other, this one here also. Okay, so I think that's all. So what remains here is we have negative 1 here. In the numerator we have negative 1, and also we have 3, and x, and also n. In the denominator we have n plus 1 times 5. Okay, so let's erase this one here. Sorry. So let's try to remove the absolute value. So and we will remain the variable n on the left side. So we have 3 over 5 times absolute value of x times the limit of n over n plus 1 as n approaches to positive infinity. Okay, and as you can notice, the limit of this limit here is 1. Okay, positive 1. So this will become 3 over 5 absolute value of x. And for this for the values of x for which the limit the what do you call this one, the given is convergent if this is less than 1, okay, by the ratio test. So simplify, or we can write it as absolute value of x, multiply both sides by 5 over 3. This is 5 over 3. Okay, or if you further simplify this will become this form by the definition of the absolute value, 5 over 3. Okay, or using interval notation we have negative 5 over 3. Sorry, so what happened here, 5 over 3 is interval here. Okay, so as you have noticed, this interval is not the interval of convergence yet. Okay, so please be careful. Let me write it here. This interval is not necessarily the interval of convergence. Okay, so what we will do here, to determine the interval of convergence, we have to test it first, the endpoints. Okay, if these endpoints negative 5 over 3 and 5 over 3 is included in the interval of convergence, but all the values here are inside of this interval are already the belongs to the interval of convergence. However, the endpoints we must test the endpoints first. If negative 5 over 3 and 5 over 3 are included in the interval of convergence. Okay, so to determine this, what we will do is we must test. Okay, we must test the convergence at each endpoint. Okay, so when x is equal to negative 5/3, what will happen here, we have this one. Just look at the given and replace x by negative 5 over 3. Okay, so this is 3 to the n times, as I've said, we have to replace our x by negative 5 over 3 times over this one, where n starts from 1 to positive infinity. Okay, simplify this fraction here. So what will happen is we will have negative 1 to the n plus 1 times 3 to the n times distribute. You can distribute negative 1 here. So we have negative here, negative 1. So substitute our n to that one. We have this one here, 5 to the n over 3 to the n over 5 over n times 5 to the n. N starts from 1 to positive infinity. So what will happen here is we can cancel out this one, okay, and we can cancel out also this one here. Okay, so what will happen here is we have negative 1 to the 2n plus 1. Why? Because we have the same base, negative 1, so n plus n is 2n over times 1 over n. Okay, where n starts from 1 to positive infinity. Okay, further simplify this one here. We have negative 1 to the 2n times negative 1 times 1 over n. N starts from 1 to positive infinity. So what will happen here? Notice that this is always always equal to negative 1. No, positive 1, sorry. Positive 1. Okay? So if we further simplify this one, we can factor out negative. This is 1 over n, where n starts from 1 to positive infinity. And as you have noticed, this expression here, this is an alternating, not alternating, this is a harmonic series. Okay, harmonic series, which is divergent. Okay, so this means that the endpoint negative 5 over 3 is not included in the interval of convergence. Okay, so how about when x is 5 over 3? So we have here summation of negative 1 to the n plus 1 times, again, replace x by 5/3 times 5/3 to the power of n times 5 to the n. N starts from 1 to positive infinity, and this will become, if you simplify this, we can of course factor out 3 to the n times 5 to the n over 3 to the n times n, this one. 1 to positive infinity. So we can cancel out this one, and we can cancel out also this one. So what will happen, this is series now is very familiar. We know that this series is an alternating harmonic series. Okay? Harmonic series, which is convergent. Okay, so 5/3 is included in the interval of convergence. So our conclusion, therefore our R is the radius of convergence is what? 5/3. Okay, and the interval of convergence is this one. 5/3. Negative 5/3 is not included, but 5/3 is included. Okay, this is what we call the interval of convergence. Okay, so why our R here is 5/3? As you have noticed in our discussion, this one here, we know that this can be written as absolute value of x, which is less than 5/3. Okay, sorry, 5/3, and we can write it in this form: x minus 0 less than 5/3. And if you recall our definition of in case 2 of the theorem, look at case 2 here. Let's try to move upward. Where's that one? Okay, this one here. So we should write it in this form. Okay, we should write it in this form. This one. Okay, so x minus absolute value of x minus a, which is less than r. So our r here is in the example is 5/3. So we illustrate case 1 and case 2. Let's try to illustrate case 3. Let's have an example for this one. Let's move down. Okay, for our third example here, number 3, we have summation of x to the n over n factorial. Your n starts from 0 to positive infinity. Okay, solution. Again, we are going to let our a sub n to be x to the n over n factorial. So again, we will use the ratio test. Then by ratio test, we will not use root test. It's very obvious in this example. We have limit of a sub n plus 1 over a sub n. So we have replace n by n plus 1, x to the n plus 1 over n plus 1 factorial over x to the n over n factorial as n approaches to positive infinity. Okay, simplify. So we have x to the n times x over n plus 1 times n factorial. Okay, then the denominator here, this will become this one per x by n. Yes, n approaches to positive infinity. Okay, so I guess we can cancel out this one here and also this one. So what remains will be this one here times the limit of 1 over n plus 1 as n approaches to positive infinity. Okay, we remove the absolute value sign because this is always positive. Okay, by the definition of the sequence. Okay, so what happened here, the limit of this expression here, this is always equal to 0. Okay, so meaning to say, regardless of what values of x here, from negative infinity up to positive infinity, multiplied by 0, this is always equal to 0. So meaning to say, we can conclude that the values of x for which the power series is convergent is the set of real number. Okay, so here we conclude that the given power series is absolutely convergent. Okay, for all values of x. Okay, so therefore here our r here is infinity, and the interval of convergence, so this is our radius of convergence, is from negative infinity to positive infinity. Okay, so this is our interval of convergence, and this is our radius of convergence. Okay, so we are done with our discussion of the power series. So for our for your assignment, okay, so for your assignment, so let's have here okay, for your assignment, it's there's that one, power series. Can we move down? Okay, this is your assignment. Okay, let's lock this one. Okay, so we have 6 assignments. Okay, thank you so much for listening. If you are not a subscriber yet, you can click the subscribe button and the bell button below. Okay, thank you so much for watching.